Now that we've put together atoms into Lewis structures, we can start looking a little bit deeper. Lewis structures have several limitations. We only get two-dimensional structural information from these, and we only see how atoms are connected. It tells us nothing about the three-dimensional shapes of molecules. And why do we even care about the three-dimensional shapes of molecules? Well, it turns out in biology, especially, this is important. If we have an enzyme that we're trying to target with a drug, we have to make sure that that molecule, that drug molecule, can fit into the site in order to either activate or deactivate the enzyme, whatever we want to happen. And so we have to understand the shape of that pocket that's available in the enzyme, and then design molecules that will fit and take advantage of different structural features within that pocket. So that is one big aspect of drug design. Three-dimensional molecular structure can be determined by using the valence shell electron pair repulsion, or VSEPR, model. This model has three key concepts. The first is that electron pairs want to be as far apart from other electrons as possible. And that should make sense because electrons having a negative charge will repel other electrons having a negative charge. The second key concept is that lone pairs will take up more space around an atom compared to a bonding pair. And the third concept is that multiple bonds, looking at double or triple bonds, will take up more space than a single bond. And that's due to the fact that there is higher electron density in those regions, and therefore they need more space to occupy. So we'll explore those three key concepts in upcoming videos. But first, we need to understand what exactly is an electron domain and how to determine the steric number about a central atom. An electron domain is either a bond, can be a single bond, a double bond, or a triple bond. Each of those types of bonds counts for one electron domain. It can be a lone pair. A lone pair would represent one electron domain. And the final type of electron domain would be a single electron. Remember those radical species that we looked at in the exceptions to the octet rule? That would be an electron domain, a single electron. And so looking at all of those as examples, we can start to count electron domains about the central atom. Take, for example, carbon tetrachloride, CCl4. We can come up with a Lewis structure for this molecule, placing in all of my lone pairs. And we can look at this and say, well, how many electron domains does the central carbon atom have? Well, remember, a domain is a bond, a lone pair, or a single electron. So this carbon atom has 4 bonds, no lone pairs, no unpaired electrons, so it would have 4 electron domains. And the steric number is equal to the number of electron domains that an atom has. So the steric number is equal to 4 here as well. If we look at the outer chlorine atoms, we can consider the number of domains for those. Chlorine has 1 bond and then 3 pairs of electrons. So the 3 pairs are each an electron domain, and the bond is a domain. So the steric number for the chlorine atom is 4. If we look at something slightly different, this is formaldehyde. The central carbon atom has 1, 2, 3 bonding regions, and so the steric number would be 3. The hydrogens have 1 bonding region, so they would have a steric number of 1. And the oxygen has 1 bonding region and then 2 lone pairs, so it would have a steric number of 3. You give it a try on this next example. Thanks for watching.